Okay, welcome to Lab 6. Hopefully third time's the charm here. I'm gonna shoot this without my face box visual this time in hopes that this will solve the issue for us. And we get to take a look at atmosphere and pressure in this lab. Pretty fascinating topics that affect so much of our daily life, in how they would relate to weather and extending outwards from there in time anyway, climate. So yeah, to dive right in, the Earth's atmosphere can be conceived of as a thin envelope of gases held to Earth by gravity. And quote unquote, our atmosphere is really what we're most concerned with or refer most to in dealing with our atmosphere is the troposphere. And this is the Earth's surface to about 12 kilometers or about 8 miles above us. And yeah, tropo is a neat root there, meaning turn or to change. It's really within this first 12 kilometers that 40,000 feet above that, there's quite a bit less effect on the troposphere. So primarily our weather systems originate and circulate within this troposphere, this first 12 kilometers above us. And we'll take a look a little bit more at that later. And I think what this image is showing is the orange layer being the troposphere. You can see how the clouds weather systems stop right about at that layer. So that's yeah, neat image from space. Atmospheric pressure, one of the key aspects of this lab we're looking at. Atmospheric pressure is the weight of a column of air above a unit area of Earth's surface due to gravity. You can think of it as the force that air molecules exert on a surface due to their weight. And at sea level, an average 1 kilogram of air presses down on each square centimeter of surface. Again, it's pretty fascinating how closely the metric system lines up. I mean, how it's just amazing that, to me anyway, that a square centimeter of surface can have such a clean unit of measurement as a kilogram. And then if we want to use the imperial there, we're looking at 14.7 pounds per square inch. So pretty significant. So measuring atmospheric pressure, this is done through an instrument that measures air pressure, or barometric pressure is a barometer, hence barometric. It's expressed as the measured height of a column of mercury within an inverted tube, and expressed in millibars or inches of mercury. At the average sea level pressure is 1013.2 millibars, or about 29.92 inches mercury. Okay, so here's a schematic of that with the inverted tube as the description referred to, with the mercury inside of it that can ascend and descend based on the ambient air pressure around it. And some of the heights there for you. So as atmospheric pushes down, it's going to push the mercury down, and that will force it to go up the tube. So it's a handy way of measuring what the downward pressure is. Here's a slide that shows a real life, if you will, model of that, an actual barometer. And some key things to keep in mind about barometric pressure is that it decreases rapidly as altitude increases. Over half of the total mass of the atmosphere resides below 18,000 feet. It's pretty significant when we think about it. Just what a tiny sliver of the overall atmosphere 18,000 feet is, and that half of it, of the total mass, resides below that. 75% resides below 35,000 feet, and 90% is below 52,000 feet. So all but 0.1% is accounted for at an altitude of 50,000 meters, or 164,000 feet. So table 1 of the lab provides the average pressure for given altitude. So copied that in here. Not that you would need to memorize any of this, but it just gives a sense of the descending nature of amount of millibars, in this case, the amount of pressure, how it drops significantly as our altitude increases. It's a good example of how handy a graph is versus a chart of this form. In this case, here we see that inverse relationship graphed out as air pressure, well, to start on the y-axis, as altitude increases, air pressure decreases. There's a very fine amount. We're on the low end of air pressure, and for that matter, air density, here on the low end of the x-axis, with the corresponding very high altitudes. So to put it alternatively, as altitude descends, as we descend in altitude, as altitude drops, air pressure increases, therefore air density does as well, and that's what we see over here. At higher altitudes, air molecules are very sparse. Some mountaineers will hike with oxygen at high elevations. And at low elevations, for that matter at a low altitude, you don't need to hike with oxygen because there's lots of air molecules. And here we see that with some more information added to it as we descend in altitude. We're seeing corresponding millibars of pressure here, right down to just over 1,000 millibars, right around 1,000 millibars at sea level. Mount Everest is drawn a little too high here. The peak's at about 8,500 meters, not at 10. But it's a good illustration for. It's a good illustration of rounding out our graph there for us. And here we see those 90%, above 99% levels of the amount of pressure above a certain altitude. So before, when I was referring to 50% of the mass of the atmosphere is below 5.5 kilometers, 5,500 meters. That's it's not to scale, but that's a very significant amount. So atmospheric pressure, we're going to use table 1 to determine the proportion of the atmospheric mass that is above a given altitude. So for instance, an altitude of 3,000 meters above mean sea level, average atmospheric pressure at 3,000 meters is about 702.21 millibars. And we could see that on our table here. So a second, we were at 3,000, I believe it said. So right here, 701.21 millibars. 702 here, so that's a typo. And we're another, sorry, there's more to add there for you. So this is how we're going to calculate then, figuring out the proportion of atmospheric mass that is above a given latitude. It's 1013.25 millibars equals 100% of the atmospheric mass. Then we're going to just a simple division, 702 divided by 1013, so use simplified expression there, times 100, so that we can get it into a percentage form, equals the proportion of atmospheric mass above. So above 69.3% of the atmospheric mass is above an altitude of 3,000 meters. Then 100 minus 69.3 equals 30.7, equals the portion of atmospheric mass that resides below 3,000 meters. So, yeah, it's interesting. We had about 50% at, well, granted it was 5,500 meters, but here we're roughly speaking, of course, but we could do this math equation and figure that out. But here we have about 30% resides below 3,000 meters. 3,000 meters, you know, you can roughly think of as 9,000 feet. It's probably closer to 10,000 feet. So if you've ever been up, well, either the two highest passes over the Sierra Nevada, in particular Sonora Pass, up Highway 108 in the Sierra Nevada. I think, forgetting the exact elevation there, but you're getting close to 3,000 meters, maybe around 9,000, and then Tioga Pass up over Highway 120 through Yosemite National Park. If you've ever gone over the Sierra there, both of them actually absolutely stunning landscapes. Highly recommend it. But that's about 3,000 meters to give you a closest to home visual, so to speak, example rather. So we also need to keep in mind how temperature decreases with increasing altitude at an average rate of about 6.4 degrees Celsius per 1,000 meters, or 3.5 degrees Fahrenheit per 1,000 feet. Feet we see here represented by the apostrophe. And this is our average or normal lapse rate. And this is really neat to see graphed out because, once again, we see the inverse relationship. So when we're at a high altitude, our temperature is quite low. There's quite a sparse density of air molecules. And then as we descend in altitude, not only does our air pressure increase, but generally speaking, our temperature increases as well. In certain microclimates, in certain zones, you could have variations to that, but it's just most generally the trend. And here we see something neat. We have the mid-latitude tropopause and the equatorial tropopause. So tropo again, same as troposphere. See at about 40,000 feet again, 12 kilometers in miles. I think we said something around 8 miles on that first slide. Much better when it's 10 kilometers, divisions of 10, because yeah, it's 6.1, 6.2 miles, 10 to 6 ratio there. 1 mile is 1.6 kilometers, vice versa. 0.6 miles is about 1 kilometer. So just some basic key numbers to keep in mind, but it's interesting because we see the equatorial tropopause at around the equator, that is to say, that the tropopause is going to be much higher. I'll let you think that one through a little bit on your own, why that might be. imagine you learned about it in lecture as well. Anybody want to get back to me in the discussion board about why they think that is? Let some of you know right away. And it's certainly okay if you don't. It'd be neat to have a discussion about it. So we can see the lapse rate formula here then, given the temperature at the surface and the lapse rate, the temperature aloft can be calculated. For 60 degrees at sea level, environmental lapse rate of 3.5 degrees Fahrenheit per 1,000 feet. What's the temperature going to be at 5,000 feet? This is quite a simple multiplication, 17.5. So in the triangle here indicates change. So imagine you've seen come up in some of your other science classes as well, but a change in temperature of 17.5 degrees. And I love thinking about this in terms of going up over the Sierra Nevada or any mountain range. Just the Sierra is so helpful because all the little towns, besides having population, have their elevation stated on the town name as well. Some of them are much smaller towns, and so it's neat to try to estimate the temperature change as you go. maybe you think maybe some of you are thinking I'm that much of a geography dweeb, but it's I don't know, it's pretty interesting, especially if you're a skier or a snowboarder, being able to think through whether it's going to be snowing at what elevation and which mountain you want to head to. So you'll get to do that in this lab as well. And so here we click that a little further to subtract the 17.5 from our 60 degrees at sea level and up at 5,000 feet. So on Highway 108 again, I think heading up to Sonora Pass, that'd be about it. About Cold Pine, Sugar Pine, just above Sugar Pine. You're at about 42 degrees Fahrenheit there. Quite a little chillier than 60 degrees at sea level. Headed out from the coast. And where this leads us to is looking at how wind is generated, really, and the effects of pressure gradients. Pressure differences at the Earth's surface are the result of unequal heating, and the pressure gradient is determined by the distance between areas of high and low pressure. And here, as the point says, this is responsible for winds. Areas of low pressure indicate ascending or rising air at the surface. These are known as cyclones. You've probably heard that term used to refer to tornadoes, which are very condensed cyclones, very condensed rising air, circulating body of air that spirals inward. It's converging at the surface, the ground surface that is, and counterclockwise rotation in the northern hemisphere and clockwise rotation in the southern hemisphere. And this is associated with inclement or bad weather, cloudy, rainy conditions, for example. Inclement means. And areas of high pressure indicate descending or sinking air at the surface. These are known as anticyclones. It's just the reverse of cyclones. Circulating body of air that spirals outward. There's a divergence at the surface. As the high pressure comes down, it pushes away, so it's diverging. These are associated with clockwise rotation in the northern hemisphere, counterclockwise in the southern hemisphere, and associated with fair weather, nice, clear, and dry conditions. I'm a big fan of those. Except I love snow as well, and we need the precipitation, the rain, to bring the snow. So, surface winds then are a result of a high and low surface pressure. Three driving forces. We have the pressure gradient force, Coriolis effect, and surface friction. Let's take a closer look here. We have to a basic schematic here in the northern hemisphere. We'll say we're somewhere over Nevada and Utah, continental high sitting there. Pressure gradient force, right, is going to move that air to the lower pressure zone to go along with the basic schematic here to the east. We'll say over towards the Mississippi. Okay, and just for an example, that's the pressure gradient force. When we have a high and a low, it's always going to move from high to low pressure, just like if you have a cold object and a warm object, that heat is going to transfer from the warm to the cold. Same thing with pressure gradient force dictates that it goes from high to low. And then you have descending air over the high pressure and ascending around the low pressure. As the air moves up, it's going to, where there is low pressure, it's going to allow that air to ascend. As it converges, right, we used the word convergence earlier, as it converges towards the center, in this case center of the L, it's going to have to go somewhere, so it goes up. Same thing as air descends over a high pressure area, has to go somewhere, so it diverges outward. We have here the Coriolis effect of the northern hemisphere being rotated to the right. These arrows are going in over the low pressure to the right as well. And what this then generates is our surface winds, which are charted here in red, drawn for us. Okay, so as, for example, as a high pressure cell, as air would be pushed outward, because it's being pushed outward in the northern hemisphere, it's going to be curved to the right because of our underlying or inherent Coriolis effect from the rotation of the Earth. I guess in a sense you could say it's underlying then. And to see those then without the pressure gradient force and the Coriolis effect, these are surface winds over a high and a low pressure cell, is what they're called in meteorology. We'll take a closer look at those. Pretty neat. See a anticyclonic circulation around a high pressure cell and a cyclonic circulation over a low pressure cell. Low pressure area, you could just imagine. And how barometric pressure gets mapped out. Just take a close look at a quick look at isobars here before coming back to the circulation. Iso meaning same, and bars. These are a line then, a bar of equal barometric pressure. So in this case, with the high pressure over Utah and Nevada, we have well, here at the very center of the cell, this whole ring around it is 1,028 millibars pressure region, right around just south of the Great Salt Lake. And then as you work further outward from the center of the cell, the center of the high pressure area, you have a equally 1,024 millibars around this whole line, and so on and so forth. So those are isobars. A map that shows pressure differences includes lines that connect points of equal pressure. These are known as isobars. Distance between isobars indicates that the pressure gradient, or the rate at which the pressure changes with distance. So a steep pressure gradient is an indication of strong winds, right? Because if there's a big difference in high and low pressure across a certain area, that's going to generate strong winds. There's a big pressure difference there, a big pressure gradient. Isobars that are spaced further apart, conversely, indicate a more gradual pressure gradient and therefore light or no winds. So in this case, right, this is if we were to continue outward across New Mexico and into Texas, very, very low pressure gradient here across a very large amount of land, of distance. So most likely this is sunny skies over, the vast amount of the western U.S. And as we move eastward, not so much, right? We start to see tighter isobars, closer together, that is. So there's going to be a higher pressure gradient generating winds. Right? Or cyclonic over the low pressure cell here, just over just north of the Great Lakes, right over eastern Ontario. So analysis of isobars and pressure patterns are an integral component to weather interpretation and forecasting. So to take that one step further then, to forecast a little bit, and take a look at these hypothetical winds as they would be generated, and we can see the Coriolis effect mapped out on these. So, for instance, this one relates to a question you'll have on the lab a lot. If we see some tight lines right here crossing over the Appalachian, the wind without a Coriolis effect would be going north-northwest. We see some tight isobars right there in a line, but because of the Coriolis effect, it's veered to the right. And then we have more of a southerly wind instead of a southeasterly. Right? Winds are named from the direction winds are named after the direction they're coming from, right? So it's blowing northwest. It's blowing north. So therefore, it's coming from the south, and that's known as a southerly. Kind of, I guess the analogy would be people are named for where they come from, right? Most of us are Californians, right? We're from California. The wind comes from there. You're named. That's where you're associated with. In this case, this would be a Nevadan wind. No, right? But it's more of a. Again, it's blowing northwesterly to the northwest direction. So the opposite of that would be a southeasterly wind. Okay. Wind without the Coriolis effect would have been going from bar to bar, but it's pushed more northward, so to speak. Not really pushed, but with the Earth's rotation, it's diverted to the right in the northern hemisphere. This is a neat weather chart for April 4th, 2011. And yeah, so with that, we'll take it to the lab. And yeah, with these pointers here I've given you about that and some of the other ones, you should be able to work through those problems and let me know if you have any questions about anything I've said here or problems that come up with the lab. Thanks again. Thanks a lot. Take care.